You get them on the line and do some here.
That's what I was asking. That would be is that why. Absolutely.
Oh. That's another. And then the line is the.
Technically not, maybe. Signifies or.
All right, if memory serves correctly, we talked about finding the domain for this thing, and that's kind of where we left off. Is that right? Okay, so we have this graph. It's a graph of a function. I don't know that we've talked about, how to verify that from a graph, but what does it mean to be a function? One answer, one output, one y value for each element of the domain, so for each x value. So, I at least kind of talk through it this way, the idea is if I'm standing here and I look straight up or down, do I see the function? Right? So finding the domain, we see that kind of the first time it shows up is at -1, and then everything included through to 2. Verifying that it's a function kind of relates to the same idea. What I want to see is that for any x value, I get only one y value in return, right? So if I go, say, here to 0 and say, hey, what's the y value that goes with 0? I look it up, I look around, I find the graph, hey, there it is. What's the y value that goes with 0? -1, okay. And there's only one of them, and that's good. Now, to verify it's a function, we want to check that for all of them, sort of. How do you do that with a graph? Using vertical lines, because x values are vertical lines. Right? This idea of, hey, stand here and look straight up or down. What you're doing is defining a vertical line. So the idea is if I walk along this graph holding, an infinite, imaginary, invisible, whatever vertical line, as long as it only hits the graph one time in any given spot, we're good to go. So this is a function then because it passes a vertical line test. Anywhere I would drop a vertical line on the graph of this thing, it hits only one time, right? Okay. Notice this would not pass a horizontal line test, right? Because, for example, right there, a horizontal line would go through 2 times. That means something else. We'll talk about that later on. But to tell if it's a function, we want each x to go to 1 y. Those are vertical lines. Okay. All right. And the domain, what we come up with for the domain of this? Everything from -1 to 2. In interval notation, we write that as -1, comma 2. The idea is where do you start and where do you stop? Right, so where do I start sort of shading this thing in, or where do I start seeing it? If you want another way to think about that, rather than sort of like where it falls or where would this, line that I'm carrying hit the graph, basically what we're doing is if I had this whole thing on like a sheet of silly putty, like I don't know if this dates me because I lived in, as a child before there were like iPads and things, right? So like maybe you don't know what that means, but if I had this on a big stretchy thing and I smushed it down like that, so it was kind of flat. The domain is the x values that get covered up. So that's everything between -1 and 2. The way, again, that you write that as an interval is to say, okay, left to right, I'm going to start at -1, I'm going to stop at 2. And then to capture the sort of endpoint behavior, that this one's open and that one's closed, Parentheses means open, square bracket means closed. So how do we find range? Do the same thing, but for the y values. So instead of squishing it top to bottom, I squish it the other way. What's the lowest that graph ever goes? -1. So the range begins at -1. And what's the highest it gets? 3. And is everything in between covered up or, included, part of that? Yeah, what's the one place where we're maybe uncertain about a little bit? Here it's 0. We're talking y values now, so the point is -1, 0, but the y value is the part we care about. Here it's 0. Why? Sorry, that's WHY. Why? It's open there, but it's included over here, right? It does get picked up somewhere. It's not right there, but it is right there, so it is included. So these should both be brackets. Everything is actually included and passes through there. We'll have to kind of modify this a little bit as we go through the semester, but if a thing looks like it goes through a point, then it does. We'll just assume that. If I mean to tell you that something doesn't go to a point, then I'm gonna like make, be really upfront about it, right? Like an open. Again, we'll modify that a little bit as we go through the semester, but there you go. Okay, f of 1, and when does f of x equal 3? I'm not gonna move this around anymore, so I'm gonna go back here. What is f of 1? Okay, why? Okay, I take the x value to be 1, so I go find x equals 1. I figure out where the graph is. It's right there. And I take y value, right? That point is 1, 0. So what this is asking is what's the function value, which is the same thing as a y value, right? We use those things interchangeably. That goes with the x value 1. So when x is 1, y is 0, f of 1 is 0. And again, that's an x. That's the y that goes with it. So this is what evaluating a function, last time we took a function like an equation version of a function and plugged stuff in, right? That's evaluating a function when you have the symbolic form, the equation. This is evaluating a function using a graph. I give you an x, you tell me the y. When does f of x equal 3? Why? Yeah, now we're doing the same thing, but the other way around. I'm giving you a y, which means I'm asking for the x. The only thing we're ever going to do, and like even if you're a math major, like you don't see functions of more than one variable until you get to like calculus 3, right? Like that's a long way off. We're talking about functions of a single variable. That means you got two things, you got x and a y, and they go together. And to find one, you have to know the other, basically, right? With a few exceptions for special cases and whatever. But basically the idea is, and this goes to those, on the syllabus, the like course objectives or whatever it's called, about like things we're going to do. And there's a very few of them. Pretty much all the time, I'm either giving you an x and asking for a y, or I'm giving you a y and asking for an x. And that's what's happening here as well. Here I'm giving you a y, which means I'm asking for an x. So we find that y, here it is. We go find the function, there it is. So when does f of x equal 3? When x is 2. Everybody okay with that? Okay. Now there is a little bit of a subtle difference in these things. Part C, what is f of 1? There can only possibly be one answer to that, right? If the thing's a function. Part D, when does f of x equal 3? That's given a y, find the x, right? There could be a bunch of those. That's like the other day when I said like, hey, who's 5'6"? Raise your hand, right? There could be a bunch of people with that function value, that could happen a bunch of times. Here it only happens once, but there could possibly be more than one. Okay, x-intercepts. What do we mean when we talk about intercepts? Where it crosses the axis. This is the x-axis, that's the y-axis. So the x-intercepts are where it hits the x-axis. So where does this thing hit the x-axis? Yeah, here's the x-axis. There's exactly one place where it actually intersects it. Because again, the other place where it's almost on it, it's just almost on it because of that open point, right? So what are the x-intercepts, or what is the x-intercept? 1. As a point, 1, 0. This is one of those places where, just keep an eye on like how the thing is asking you to answer it, right? If it wants to order pair. 1, 0. Typically, it's fine to just say the x-intercept is 1, and we know that because it's an x-intercept, that means it's on the x-axis. What's the y-intercept? -1. Again, I'm just going to write it as a point, 0, -1. Okay. Pretty feel good about all that? Anybody have any questions? Okay. And remember, what's the only bad question? Okay, cool. Well, if we all feel good about things so far, let's just real quick do one more similar kind of thing. Don't worry about, stuff I'm typing in. Here's a graph of a function. Make it a little bit easier to read. There we go. There's a graph of a function. Oh, sorry. Here's a graph of a thing. Is it a function? How do you know? Apart from the fact that I just said it like 6 times in trying to set things up, because it passes a vertical line test, right? If I march along this thing with a vertical line, that vertical line only ever hits one time. Again, I probably said this last time, but we're going to assume that what we can see for any time we're given a graph, what we can see is all the interesting stuff that happens. So where it goes off the edge of the graph there, it's going to keep going up and to the right forever then, right? There's not like, oh, surprise, some weird thing happens way out here that Dr. Thomas is trying to trick us about, right? So this passes a vertical line test. That means it's a function. What's the domain of this function? Y1 to infinity. Because in terms of the x values, it starts at 1. If I smush this thing down onto the x-axis, the stuff that would get covered up is over here. So from 1 to infinity. How would you write that domain? Sorry. Beginning at 1, continuing to the right. So from 1 to positive infinity. Is 1 included? How do we know? Because it looks like it is, and because I didn't give you an open circle to say it's not, right? Again, later on, there'll be times where we have to fill in a little bit more. For now, I'm going to shout it at you if it's not included. So square bracket at 1. What about infinity? Right. I mean, I did already write it, but why parentheses at infinity? You can't capture it. You can't get there, right? Square bracket means go to this point and then stop, right? Like if I said, hey, go like walk up to the wall. I don't know, that's weird, but like that, right? You can't get to infinity, right? Infinity is a concept. It just means keep going. So always parentheses there. What's the range? 3 to infinity? Second. Okay, bracket at 3 to infinity. Good. You feel okay about that? Okay. What did I just change? The range. I didn't change the domain. The range changed, right? What's the range of this thing? Now it's pointing down. So 3 isn't the lowest point anymore. Now it's the highest. So the range should look like parentheses negative infinity to 3 to the bracket. What's your question? All right. Negative infinity to 3. You read interval notation the same way you read a number line. So if negative infinity shows up at all, it's on the left. If positive infinity shows up, it's on the right. It has to be because that's how you set a number line up, right? Okay. So x values, domain, we read left to right. Y values, do the exact same thing, only when you look at it, you turn your head like this and you look at it bottom to top. All right, pretty good? Okay. Kind of more menacing when I ask it and then point at you with this, right? Okay, well, we are going to look for kind of the rest of the week, the next couple days. We're going to look at graphing in more detail. We're going to talk about some properties of functions related to symmetry. To start that, we're going to look at our first kind of like concrete example of a specific function type. It's f of x equals x squared. This is also called the squaring function because what it does is take a number that you give it and square it. Right? And what does squaring mean? Take two copies of them and multiply them together. Right? So if I plug in 3, that's 3 squared, that's 3 times 3, that's 9. Okay, so what I want you to do for, 5-ish minutes or something, is, together again, take a look at it and try to answer these things. Don't necessarily feel like you have to go in this order. If you want to start with the graph, throw it in the calculator or Desmos. Sketch and pay attention to track coordinates of a few key points. So plug in, for example, a few values like that, and then look for patterns, find the domain, find the range. I'll probably need to fill in that blank for you, but I'll take a couple minutes and think through that.
I mean, it's x squared, like, you don't have to even have it. You can just sit down, okay, yeah. Negative infinity. Right.
You're going down.
Opposites. Yep.
Maybe for
I can do so for example.
I would. Oh, wait. I get the one.
Think through it and write it down. Right, because negative 2 times.
Negative 2.
Yeah, okay, got it.
Can't have it on here,
Okay, oh wait, but I.
because it never goes below.
Right, yeah, you can, you're right, but yeah. So think about what that will look like. I get almost having a 2.
And I would think,
So, negative x.
like what is that push?
So the same way you would write
Thank you. Oh. Maybe.
That's why.
Maybe that's like interesting.
I find that negative value of any x. So it'd be negative, when negative one, it's equal. It would be. Definitely. Plug in a negative x, you're gonna get a positive y,
Okay.
no matter what.
Let's see.
That doesn't make sense. That's y.
That's positive.
The negative times negative. And one times negative one.
My phone doesn't work. So it's sort of a lot of stuff.
Yeah, well, I mean. Like this. Think it's okay. You go this way. You just plug in any negative number of it. And then put your.
Gonna call it out. Thank you. Do you notice anything about these folders? They reflect anything?
Okay. So, you have to tell us because.
That every time I look.
Okay, yeah, there's a, like, privacy settings. Thing that they're.
I have my own. Hooked up. My second one, because I already lost that.
Basically,
But they
telling
talked
you
to
that
email
it's gonna
actually.
allow.
For someone. But I'm still stuck. 15 So I thought I was gonna hop on Hazel. And she just said a lot like on campus. I mean, really.
Okay, so if we plug in a few x values, for example, those 5 I gave you, you get 4, 1, 0, 1, and 4 as the y values go with it, right? The function squares whatever you give it. That means it takes 2 copies of those and multiplies them together. That means if you start with a negative, you end up with a positive, right? So -2 times -2, for example, is +4. So there you go. Now you do that for all points, even the messy ones in between, and you get a graph that looks like this, right? We'll talk a lot more about these later. We'll spend like, our whole, like chapter 3 basically is about this type of function, but the shape of the graph is called a parabola. They're important for all kinds of stuff, but for now, it's just, hey, here's this graph of this thing. It is a function, right? Because this is a vertical line test. What are the domain and range of this function that looks like this and has ends that go like that? Yep, for the domain, because if I, again, squish this thing down or flattened it out or whatever, what's covered up along the x-axis? Everything, right? That end's pointing to the left, this end's pointing to the right. If you want to think about it as like operationally what's happening, what kinds of numbers can you square? Well, any of them, right? I know how to take 2 things and multiply them together. That's fine. So the domain is all real numbers, or as an interval, -infinity to infinity. What about the range? 0 to infinity. The lowest it ever gets is this point right here at the origin. So the range is 0 to infinity. The ends are pointing upward. 0 should be a bracket because it's included. It does actually pass through that point. Okay, cool. All right, now part D, right, is where things, kind of go up a level in complexity and what it's asking for, right? Do you notice anything about these points? They're also operating on the buddy system, right? Every point is the mirror image of another point on the opposite side. Why does that happen? Because we're squaring, and what happens when you square negative? You get a positive. What happens when you square positive? Also get a positive. So it's helpful a lot of times to think of positives and negatives as just being opposites, right? In the like number line sense. Positive 2 means go 2 that way. Negative 2 means go 2 that way. Okay? So positive 2 and negative 2, I think of those as opposites of each other. Their, center, the middle is 0, right? That's what's halfway between them. So that's the y-axis. Here's the y-axis. This point and this point are mirror images of each other relative to the y-axis. Way to say that is that this one is the y-axis reflection of this one. If I hold this line still and flip it, I get from this point to that one and vice versa. Now notice, since that happens with not just those points that I marked, but all the messy points in between, this whole branch of the graph and this whole branch of the graph are mirror images of each other. If I, drew this really nicely and, on a piece of paper, folded it over the y-axis, those two sides of the graph would, sit like that. I can't think of, but those would be in the same place, right? What we call that is y-axis symmetry. The y-axis acts like the middle or acts like a mirror for the two sides of this graph. All right, what happens if we try to find f of negative x? If I plug negative x into this function, that says take negative x as a single whole, quantity and square it, which means multiply it by itself. And what happens? The negatives go away. You get x times x, and x times x is, well, another way of saying x squared. But the whole thing we've been doing is talking about x squared as a function called f, right? What I'm doing here when I plug in negative x is I'm saying, don't get hung up on the x thing. I'm saying, hey, this thing that we noticed about 2 and negative 2 and 1 and negative 1, that would have happened for any value that you picked, and it's opposite. So if I found f of 17 and f of negative 17, I don't know what 17 is. Well, I do know what 17 squared is, but like I can find 17 squared. That's not the important part. 17 and negative 17 would be in the same place. Yeah. Messy decimal 1.743, whatever, and it's opposite. Those would be in the same place also. That's what this says. That it's not just a thing that, just so happened to work out for 2 and negative 2 and 1 and any of in the domain, which is all real numbers, so it means everyone. So f of negative x, this is saying, hey, I'm gonna think about a point over here, and what I want to figure out is what does its opposite do? The point across from it, across the y-axis from it. And what we found out when we worked things out is that what this does is the same thing as what this does. So that point over there, 147, and this point over here, negative 147, those are in the same place. Now, I don't know how tall that is because that's a big thing to square and I want to do that, but they're going to be in the same place. That make sense? But so the difference is when we plug in 2 and -2, for example, we're showing an example of what happens. When we do it with a sort of generic variable, we're really proving that, oh, it's not just some trick of the arithmetic. This is what's actually happening. That kind of makes sense. So that level of like abstraction tells us more about what's going on. Yeah, it's a good question. Thank you. This is what the algebra looks like for a function that has y-axis symmetry. So y-axis symmetry, that's a like graphical property, right? That says, hey, if you fold over the y-axis, you're going to get a mirror image thing that shows up the same way. This is what that looks like in the algebra, in the symbolism, right? That those things are the same. We have a name for that. Those are called even functions. Things like x squared, x to the 4th, x to the 6th, x to the 12th. Notice all the powers I just said are even numbers. Those have this same property. There are other things that do as well, but that's a way to kind of keep track of the even thing. X squared is a good example. It's an even function. It has y-axis symmetry. Back on the like front page of the notes, that's one of the definitions that we had kind of left off until later. It's later now, so you can go fill that in. Even functions always have y-axis symmetry, which means they also always have this property, that f of negative x and f of x are the same. Questions so far? Okay, well, do the same thing with example 6 there. The cubing function. I talked to several of you already that kind of figured this out on your own already, but if you're using a calculator to try to do the arithmetic, you probably need to throw a set of parentheses around things before you cube them to make sure it's doing operations in the right order. Okay.
So now I understand what you guys did. This one is. So here, the X value is like that. That.
Is there a time?
Round that.
Yeah, correct.
Baby. I was thinking out loud, because this would be negative X. Because if you plug in a negative value, they're here to make it. Oh, you're right there. So you gotta think about what value you plug. Which would be called, yeah. This is what this is. Oh, what? Yeah, it's like. Ooh. It makes sense. Whatever that is.
Yeah.
Is what. But that means that I have.
So. If you miss. Yeah. So, for example, this week.
So you know what? You guys
Yeah, so-
understand the, after they put the key.
Right.
Okay.
Earlier, we did for amplify this one.
This is my.
One thing I noticed is that any positive are always gonna be, but in the negative.
But do you know how to break that? But it really. That, where the negative.
Because that would imply that every x is gonna be a negative.
Interesting stuff to think about in the future. And we're gonna assume that like mine is gonna. Again, we'll have to kind of decide that. when we- We continue.
It's not symmetric, right? Not even that. Oh, okay. It's the same number, you know.
You could do that.
It's two and eight.
Like there's no.
I think it's the same number, it's in
I just gave you a couple of points.
yeah, that's.
Okay, wait.
Negative. So.
I'm just wishing it was something. Oh. The direct example of.
Okay. There is a graph of X cubed with, again, a couple of example, let's just see what these points look like, points marked, right? There's nothing special about the 5 X values I gave you, except that they're close to the sort of center of the thing, right? And give us kind of something to look at and be some points to point at, right? So when you take -2 and cube it, that's -2 times -2 times -2. You multiply a negative by a negative by a negative, you get a negative, okay? They cancel in pairs, right? So, and 2 times 2 times 2 is 8. So -2 cubed is -8. -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So there you go. We've got these few points that I can point at. And again, all the messy stuff in between, that's there as well, right? But it feels cruel for me to be like, find a couple points. For example, I want to know what point 1 choice, right? And points beyond that, outside of that scope, those are included too, right? You could take -4 and cube it, or negative a bajillion and cube it. We just didn't because we're just trying to get a feel for what the thing does. The ends of this thing, sort of go off smoothly. If you graph the thing in a calculator and start zooming out, you're never going to see it like stop or cut out, right? So, what does that tell us about domain and range? If I flatten this thing out onto the x-axis, this side of it, flatten out like that and point to the left. And pointing to the left means negative infinity. This side would flatten out this way and point to the right. And pointing to the right means positive infinity for the domain. What about the range? Same thing, only turn our head sideways. So the, starting point for the range, I see an end that's pointing down, which means, and an end that's pointing up, which means positive infinity. It doesn't start or stop anywhere, it just is, right? It keeps going. This is defined everywhere. Okay, we sketched some points. Do you notice anything about these points now? Everybody's still got a buddy, but they're a little more, I don't know, confused, right? There's still some mirroring, some symmetry stuff going on, but what's acting like the middle? It's not the y-axis. If I flip over the y-axis, I'd get a thing that goes like that, right? And that'd be the same thing for the x-axis, actually. So if I mirror over the y-axis, I get a thing that looks like that. Well, sorry, before it snapped to a line. If I mirror over the x-axis, this point would end up down here and vice versa, and I end up with a thing that looks like that. So it's not either of those things. It's not either of the coordinate axes. How do I get from this point to this one? I have to kind of go upside down and backwards, right? Or rotate it. This one to this one. If I rotate around, what's staying still though? 0, the center. So this is called origin symmetry. The idea is that if I put a pin in this thing at the origin at 0, 0 and spin it upside down, that's how the symmetry works. Yep. Yeah, origin symmetry. So basically that's either reflect over the x and y-axes, or put a pin at the origin so it's 0, 0, and rotate the thing 180 degrees. So if I stick a pin, a tack in the paper right there and spin my paper upside down, the stuff that was up here ends up down there and vice versa, right? I end up with the same graph. I can't tell the shape of the curve apart if I spin it upside down, right? Or you could just, actually turn your head upside down and the picture looks the same now as it did before, only on my right it doesn't make any sense anymore, right? But the picture's the same. It's sort of rising from left to right. Yes? That's origin symmetry. If I plug negative x into this, so where there was an x before I put negative x, and then I cube that, what happens? Negative and negative and negative, so it ends up being negative. And how many copies of x did I have? X times x times x, so 3 of them. which I should write as x to the third. So what's happening is that we're changing order of operations, right? The negative pops out of the parentheses. Now it happens before the exponent does, which is the same thing as taking the function f of x and just throwing a negative sign out in front of it. If the other thing was called an even function, what do you think these are? So again, for our purposes, odd function, origin symmetry, these are kind of different aspects of the same property, right? Origin symmetry is a graphical thing. Saying a function is odd is kind of a property of how the function behaves in the abstract. And then this f of negative x equals negative f of x. That's the like analytical or symbolical kind of version of the same thing. But for our purposes, they all mean the same thing. So if I'm thinking, you know, sort of definition, odd symmetry, odd function, origin symmetry, and f of negative x is equal to negative f of x. Okay. We will call it a day there. Tomorrow we'll, you know, pick up and work some more examples for verifying where things are even or odd and figuring out how the symmetry works. Between now and then, if you haven't already, get into the homework, make sure you can log in, get started on stuff. You should be able to do the majority of it at this point. I'll see y'all tomorrow. Yes.
So,
Just half a second.
so can you explain